Yes, my name is Miloslav Kepka. I'm from University of West Bohemia in Pilsen, Czech Republic, and I would like to present results of research work which was done by my younger colleague in collaboration with our friends from University of Technology in Bratislava and in collaboration with the industry. At first, let me introduce our research center with the name Regional Technological Institute. This research center was established 10 years ago at the Faculty of Mechanical Engineering. And in 9 laboratories now we have approximately 80 full-time equivalents dealing only with research. And part of them are dealing with additive manufacturing. In one laboratory, we have equipment for application of printing the polymers and composite, and I will speak mainly about the laboratory of metal additive manufacturing. We are equipped with 2 professional equipment from company EOS. One of them is equipped by in-situ monitoring system, and the third equipment is used for education of our students. We have open licenses for 4 types of materials, and EOS, we use a direct metal laser sintering technology. We are very happy that we can perform a lot of post-processing operations after the printing in one house, because the rest of lab are equipped for mechanical properties investigation, for surface treatment, heat treatment, very deep metallographic analysis, etc. Because we are on the market for more than 10 years in education, R&D, and collaboration with industry, we perform for all our licensed material a lot of fundamental research. We studied the orientation of printing, influence of a microsurface, influence of heat treatments. Still, we are investigated very intensively influence of residual stresses, and we are looking how to decrease these residual stresses, for example, by preheating of a platform, etc. I'm not expert in additive manufacturing, but I collaborating with my colleagues and because we presented our results to the industry in our region. And our industrial partners still ask us, please apply this technology for the components. And what is the problems with this? How to design the components? What's the price of the components? What are risks of the components? And I am very proud that we have printed many components, mainly for maintenance and repair, some machines and equipments. And I'm very proud of our own development, because we have some components we developed and protected and patented across the board. Some of them were very high evaluated, not only on national level, but on international level too. For example, this smiling head with a trade name Kraken. I will show you this later. But what's the problem? I'm very proud of this application, but still I feel the problem is the fatigue of the components. And I feel 2 main aspects. For example, one is that there are no big relationship between the tensile strength. It's not possible to start design with knowledge of basic material properties, because the fatigue life cannot be estimated from tensile strength. And the local stresses are often multi-axial, even under uniaxial loading due to the complex shape of the components, because additive technology has a reason only if we use the optimization of the components. If we look for the shape, which is very free, and we spare the weight, it means we have a lot of local stress concentrations, and in this concentration we can find multi-axial stress state, and in operation many components are exposed to multi-axial loading. It was the reason why I asked Czech Technological Agency to perform the project according investigation of printed metal components and exposed to multi-axial fatigue loading. We performed it in collaboration with a small Prague company, dealer of the Siemens software, and performing many optimization. Our university was responsible for printing the test specimens, and our friends in Slovak performed the tests and evaluation. On this picture, you can see setup of our research. We investigated two materials, managing steel and stainless steel. We printed a test specimen in vertical position with default parameters of the EOS machines. Preliminary, we investigate the potential shape of the test specimens. Finally, we decided for version A. You can see the dimension. It means we tested component-like test specimen because it was a hollow round sample in as-built condition. We used between 10 to 12 specimens for each type of loading, which was performed by MTS machines at tension compression regime, torsion, and then some multi-axial loadings. Some of them was proportional and some of them was non-proportional. In all cases, sinusoidal wave of the loading. The failure condition was the total rupture of the specimens. We evaluated the basic SM curve. My colleague Vladimir mentioned that in some cases SM curves at the normal and shear stress are not parallel. It can complicate it using some multi-axial criteria, and then we interpret results in position of experimental versus estimated value in this diagram I showed you. Our friends in Bratislava used 4 criteria because in this experiment we followed previous work performed by our friends in Bratislava in International Journal of Fatigue. It was not printed specimen, it was a standard steels. And then we evaluated results of this investigation. In our contribution to the proceedings, we can show the specific value, but I think very useful is this type of interpretation because now we have some, how to say, image, what is the trends of various multi-axial criteria when we use different loading with the different materials, which criteria is in tolerance band, which criteria overestimates or underestimates computationally performed estimation of a fatigue life. This is a very good background to follow to some specific components. We still try to optimize our best product. This Mylink head Kraken. You can see 2 new versions which fulfill again condition we prescribe for this components. And in the next 2 or 3 slides, I will speak about the components which is below. This is a components for investigation. It motivated as a Škoda transportation. This is a part for a very complex area of a tram. very near the body, it's necessary to install protective frame because this frame protects body against the knee and against some non-expected subject on the rail track. And yeah, our task was to replace these components, which is casting, and to produce the components with lower weight and with the same or higher stiffness. It means my colleagues perform a lot of steps with topological optimization, and then we investigated the stiffness. We tested cast version, printed version with the same shape as the cast version, and then we tested the optimized component. We can say that we are able to spare 40% masses with the same stiffness. Fatigue life of the components will be performed by only fatigue life calculation, but what I must say, because the components operate in very, very different environmental conditions, because the temperature is changing in operation of a tram, the components is exposed to the corrosion. Yeah, it is the reason why we, in collaboration with another partner, investigated the fatigue life of both steel, again, at different temperatures and in non-corrosion and corrosion environment. It's not surprising that stainless steel, because it was developed for this type of situation, has not big changes in SN curve, but managing steel, yeah, there are very important differences between testing at different temperatures and logically at the corrosion equipment environments. This last slide is from another project in which we try to apply the thermal spring on printed components. And because we started again with the managing steel, together with Opole University of Technology, we perform both working place own fatigue tests of the managing steel, and then we look for data in literature which describe very, very similar conditions as we perform together with Adam Nieslony. And what I think that we have to evaluate statistically very huge data to find the design curve and recommend to our partners in production companies to use this design curve when we try to develop the new components and be on the safe side. I have no conclusions because my presentation was not so scientific, maybe more motivated, but I hope you enjoy my non-scientific presentation. Thank you.
Thank you very much. Are there any questions? Just one.
Only comment.
Microphone is okay.
This is a light question. If you can formulate the most important problems of AM technology for application in industry in today, most important problems, which is the
most important problem, I think, is many parameters which you can change during the process, and many parameters which can influence final mechanical properties. But as a no professional expert, I feel that, for example, heat treatment has a very big influence for final mechanical properties. And of course, surface conditions, because our knowledge is, this is a very general interpretation, that the most of the effects are on the surface and very near the surface. This is our knowledge from inside monitoring the processes. It means if you use some mechanical treatment and you have not as built component, you have a very good results. This is a theme from many pictures in literature and here at this conference too. This is my
Yes,
general view.
okay, that the higher level of standardization can be
And yes,
Can you
yes,
assume?
the standardization, I think, is one very important way how to say normalize the results. Sometimes it could be very useful during the scientific work to show all parameters which was performed. Because, for example, the second using the powder, it can influence totally the results. Yeah, and aspects which is investigated is on the second level. Yeah.
Okay.
Yeah. Thank you.
So thank you again.